Yeah, the whole concept of matching like the Gale-Shapley algorithm is really, really interesting. And I,
Hmm.
I think like moving more onto the computational side, like a lot of your work also mentioned like transparency and like decision making and explaining that within AI and
Yeah.
machine learning models. So I guess like how would you like approach like the whole like idea of explainability and like ensuring that models are transparent and trustworthy?
Um, Very carefully. This is the short answer. It's a very hard problem. Um, Generally speaking, there's a lot of different approaches in the literature. Um, One of the maybe easier ways to cut or to kind of understand that space is there's what's called feature highlighting or model highlighting, more generally explanations that basically tell you here are some interesting aspects of this predictive system that has that we think or we're doing this kind of like external like auditing or examining of the algorithm from kind of the outside. These are parts of the algorithm that we think have caused it to make a certain decision. um, and that's really important because there's a lot of really interesting things also happening now in the legislative space, both in the US and the EU and other places, that basically say to AI systems designers that, well, you gotta make sure that people understand why your predictive system works the way it does. um, and we will have to, this is a technical challenge to build systems that are able to highlight certain aspects of the predictive model, right? And indeed, to some degree, assure that what we are identifying are indeed causal relationships. There are so many questions in this space that are actually quite challenging to even answer. For example, is an algorithm using certain information that it's not supposed to be using, right? For example, is it using a certain protected feature, right? So think about like gender or ethnicity. In some contexts, you do not want an algorithm to make predictions that are based on those features, right? So think about like, for example, in offering people loans, right? So you want to make sure that a financial decision is not based on, like the people get their loans rejected just because they are of a certain gender or of a certain race. That's undesirable, obviously. So, but the question of is the algorithm using it? Is it using that information is actually quite challenging, right? So it's not that obvious. Like, what does that even mean, right? So you need to be a little bit careful about that. Um, that's on the feature highlighting side. And the other side of things is what's called algorithmic recourse or counterfactual explanations. And that's another very interesting field um, that basically says, okay, let's say that, me, Yair, I applied for a loan at a bank and my loan got rejected, which is unfortunate. What can you do? And then I realized that what made the decision, like it was some automated decision maker. And then I asked the bank, well, what could I have done? What is it that I could have done in order to change the decision of the algorithm? Um, and then ideologically, what should happen is that the, the bank would supply me with what's called a counterfactual, or saying something like, well, if you had changed those elements of your application for the loan, then you would have gotten a different outcome, right? And then the question is, well, how do we generate these kinds of counterfactuals? How do we generate them in a way that they're what's called actionable? So by actionable, we simply mean that, well, a user can actually follow these recommendations, right? If I ask you to do stuff that's either impossible or really, really difficult for you to do, then you probably won't follow the recommendation. Or if I ask you to change really a lot of things, right? So if I asked you to change, I don't know, 15 things about your application, that's a lot more challenging than if I had asked you to change, let's say, three. So there's a lot of really interesting questions that you can ask about what kind of a system am I going to design in order to come up with a reasonable counterfactual explanation, one that would be kind of like successful, right? That would actually cause a change in the outcome. And there's some uncertainty because, well, machine learning models can be really weird and complicated. It needs to be actionable, so a user can actually do it. You need to have something that's maybe sparse. There's a lot of other desirable things that you want. But this is just to give you an idea. There's also other questions that we're examining, for example, around the fairness of algorithmic recourse. For example, you don't want it to be the case that certain groups get a disproportionately more difficult counterfactuals than others when there's no real reason to do it, right? So, like that's another question here. And of course, the entire AI landscape is changing really, really fast. So, for example, you can ask, well, how do we explain the outputs of an LLM, right? A large language model, right? So, like ChatGPT or stuff like that. It could be really, really complicated because those systems are, I mean, they're really, really like orders of magnitude more complicated than prior work. So you want to be like careful about what you do with them. How do you explain their behavior, and that is a real challenge.
Yeah, actually, on the topic of large language models, like you mentioned, like the counterfactual like explanations. Do you think
Mhm.
that language models could also like play a role in generating these? Like if you give it like a model and give it features and give it like perhaps like if with the example of the person who requested a loan, if you
Mhm.
give it that example, could you have like a large language model generate like a reasonable explanation as to why they wouldn't get it?
So yeah, so there are works that do that. There are some works that we're also working in those directions of like trying to utilize the power of LLMs to create explanations and to do that kind of work. I mean, we're not the only ones in this space. There's a lot of really amazing researchers working on this, but there's the main concern with doing that though, and this is something that we are running into, and other papers in the literatures, other researchers find, is that you got to be a little bit careful because you want to make sure that the LLM is creating something that's faithful, right? So it's not like people call this hallucinations, right? So we want to make sure that it's not hallucinating an explanation, or coming up with stuff that's frivolous or is not connected at all to what is actually happening, and that's not desirable. So we want to make sure that happens in a consistent way. And again, it brings us to the question of trust, right? How do we make sure we trust these complicated AI models? I mean, if we don't trust them to begin with, then how do we trust them to generate explanations that will make us trust them more, right? It's like it's like this interesting question to ask, right?
Yeah, absolutely. I find it very interesting how LLMs are developing right now, especially so rapidly in the recent 3 to 4 years, and how much uncertainty is really surrounding them.
Mhm.
And that actually leads to a bigger question specific to you. What motivated you to pursue research at the intersection of game theory, fair division, and AI?
Um, I I think that what motivated me to get into game theory and fair division is just that I really enjoy like these topics of formally studying strategic interactions between people. I mean, I've been doing that from a relatively young age. I mean, we've been playing like in my family, we've been playing board games and chess, backgammon, Monopoly, Settlers of Catan, like all of these very different board games from a really young age. I still really really enjoy it. I I think that is what attracted me to the field. I think that there's really like very very deep questions that can be answered using economic language in AI, and I think that's what um, caused me to make that kind of connection. I think that there's a lot of really interesting questions because every single time that you have, a large distributed system where the people involved have their own interests or their own utilities, then um, you almost have to talk about it in a game theoretic language, right? Like it makes it very difficult to have a discussion about those kinds of systems without using game theoretic language, which is why I think it's valuable to bring those kinds of insights. Um, so yeah, so and so that's what also attracted me to, like, reviewer assignment, course allocation. You can also think about shift allocation. There's a broad kind of like space of problems here, but generally the idea is that these are large distributed systems where people have their own interests and wants in the system, and how do you account for those, right?
Mhm. And for kind of like the more future perspective, what exciting like projects or research directions are you currently exploring, and what can you expect from your work in like the coming years? So,
um well, we're working really on in the space of fair division. We're really trying to work on understanding the relationship between um, the complexity of user preferences and our ability to design algorithms that compute reasonable solutions, right? Reasonable assignments in this space. So you can think about, for example, um, the simplest possible way of expressing your preferences is to just say, I give you a pile of items. I ask you, well, just tell me which one of these do you like and which ones of them do you not, right? So you have this kind of like simple approval, disapproval model, right? But you can think about more complicated ones. You can think about, well, okay, maybe I would ask you to divide these items to items that you don't like, that you're okay with, and items that are really awesome, right? And you have three piles. Or you can think about other more complicated stuff, where you can think about, for example, problems with constraints, right? So if we think about, for example, again, in course allocation, then some students, they might like a seat in a certain class, but if you give them another seat in another class that the schedule conflicts with the class you already gave them, then they have no benefit from that class you gave them, right? So they wouldn't want it. That creates this kind of like combinatorial structure. Or maybe, I mean, another simple example is, well, students are not allowed to take more than a certain number of classes in a certain semester, right? So there's an upper bound. So it's not like you can just keep on giving a student classes and then they'll be happy, right? They'll just, at some point, they'll say, look, I can't take this many classes. My happiness stops, right? And or you can think about like even simpler stuff, like if I already gave you a seat in intro to algorithms, giving you another seat in intro to algorithms does nothing, right? So like duplicates like don't make sense here. So using that kind of combinatorial structure is also quite interesting, and we're also exploring other kind of combinatorial constraints here. Um, what lies ahead in the future? Well, I really, really hope to see some of these algorithmic systems actually being used by universities or by hospitals or Starbucks or whatever, like seeing like some large system deployment of these kinds of algorithms. I think that would be really exciting and fun, and I'm trying to work towards that. Um, and I think that in terms of algorithmic transparency, I think that there's a clear move here towards explaining really complicated, what's called foundation models, and all the challenges that come with that. I think that there's also a lot of really interesting questions involving the privacy guarantees that you get from algorithmic explanations. And here, what I simply mean is that, well, if I get an explanation, then I'm receiving a little bit more information about the underlying decision-making process. And the concern is that maybe if I get enough of these explanations, maybe I could actually infer stuff about, for example, what kind of data was the algorithm trained on, or how does the algorithm in general make decisions, or stuff that I, as an end user or kind of like some other stakeholder, I'm not supposed to know, right? Because it will be private information, maybe proprietary information, and we really don't want that to happen. So how do we ensure that on the one hand, explanations offer meaningful outputs to users, and on the other hand, they don't offer them so much information so as to actually compromise the integrity of the system, right? So that's other kind of like stuff that we're looking at. And another thing that also kind of like I draw on from economics is ideas that are related to what's called an axiomatic approach to deriving solutions. And here, what I simply mean is that, well, instead of just fixing a solution and saying, okay, this is the candidate solution, let's try to figure out why it makes sense. then you start the discussion from, well, what kind of properties do we think that a model explanation should satisfy? Right? It doesn't have to be a model explanations, but in this specific instance, right? So, like, what kind of properties should it satisfy? And you can say, well, okay, we think that any model explanation should be, if we're talking about, for example, outputting a number signifying the importance of a certain feature, then that number shouldn't depend on the coordinate of the feature, right? That it's feature 17 or feature 32, right? As it's encoded in the system, that should not have an effect on the importance of the feature, right? Or for example, if two features encode the same thing, right? If they're kind of symmetric, then they should have the same value, right? They should have the same importance. Or maybe if a feature has no bearing on the decision output, then it shouldn't get any importance, right? It should have a value of 0. So things like that are just examples of like certain axioms that we have used before, we can be using in the future to just understand better what kind of guarantees we can and cannot offer on like model explanations. And that is another thing that I'm very interested in.
That sounds really exciting. We look forward
Oh,
to your work in the upcoming years. But
thank you.
for like a final kind of fun question, what is your favorite video game?
What is my favorite video game? Um, I really enjoyed Civilization. That was really, really fun. Um, like I think I've played them all the way from 1 to 6, and so yeah, so I really enjoyed that. I really like also like the more recently like the Legend of Zelda, like Breath of the Wild, Tears of the Kingdom. That's uh that's also really, really fun. I think that like they've done. I really think they've done a really good job of kind of like creating this immersive environment. It's really fun. Like it's not like there's a lot of side quests, but they don't feel kind of like too distracting or artificial. Like I really think it's a well-made game. So
Yeah,
yeah,
there's some classics like Breath of the Wild, like all those other games are really, really good.
yeah.